All right, now let's talk about non-blocking communication styles. These have a place, and that place is mostly with out-of-process dependencies, such as in a microservices environment. You may use these in your monolith, but mostly it'll be when you have some out-of-process dependency that you're working with. When you're trying to communicate between modules, you generally don't need this style of non-blocking communication. What does this look like? Well, let's say we have module A, and module A needs to communicate with module B, needs to send it a command. All right, so we're going to use the bang operator to represent a command. Now, it turns out that module B is unavailable. And when module B is unavailable, that means module A is unavailable too, because this is a direct call. This is a blocking call in this case. So how can we fix this? Well, if we want A to always be available, even if B is not, we can introduce a queue in between. Now in this scenario, A is going to just drop stuff into a queue with all the commands, and B, whether it's up or down, it doesn't matter. If it's up, it's going to process those things as quick as it can. If it's not up, well then they'll just sit in a queue. But A can continue to be responsive. So this is how you can trade uptime and availability for consistency. Right? In this case, the system may not be consistent because we haven't actually processed those commands that are sitting in that queue, but A remains available, and the overall system may be more available because of the introduction of this queue. Now remember, inside of your monolith, if the system has crashed, if the server is restarting, if the internet is down for it, then A and B, being both in the same process in the same module, are both going to be down anyway. So introducing a queue in between these two is not really helping things as far as availability, because they're both coupled to the same hosting environment that your monolith is hosted in. But just the same, let's continue and think about how this would work with a query. All right, so now A is going to send a query to B, signified by a question mark, and B, if it's up, will return back a response, and everything is great. But what if B is down? Well, if B is down, then that query never gets a response, it blows up, and A is down. All right, now we can't necessarily use a queue for this, or if we did, we'd have to use two queues, like we talked about earlier, but we do have other patterns that we can employ. In this case, A could have a cache, maybe it's Redis, maybe it's a certain table in its database, that contains the data that it needs from B. And B will periodically send commands to that cache to update its state. So maybe on a scheduled basis, or maybe using events every time a record is updated or deleted or inserted into B, it will update the cache so that it corresponds. Now, again, this is a trade-off between consistency and availability. What if the cache is down, or what if B is unable to send its commands to the cache? Right? If that link is broken, that means A is still available, but it's not providing the latest values. If B sent a record to the cache to say, hey, this book now costs $1, and in the cache it said that it costs $10, and for whatever reason that message doesn't go through, well, A is going to continue to tell everybody that that book is $10, and it won't be apparent that it's actually been updated to 1 until the system is completely up and available again. So in a microservices architecture, this type of thing happens all the time and is helpful for maintaining availability. But again, in your modular monolith, it's probably overkill, because when B is down, you're not going to have A up anyway. And having this extra moving part of having a cache involved is probably just going to add more complexity and brittleness to your application. Now, we're still going to build it in this module so you can see how it all works, but you probably don't need it in many scenarios. So just keep that in mind.